Lab on sound tubes, lab 7 for physical science, and what we're going to be looking at is wire in a vibrating tube. An example tuning fork, and what we'll get is if we have a tube like this, if it's open at both ends, we call an open tube. If it's closed at one end, we call that a closed tube, because the sound will bounce off the bottom, but we have to keep the top open like a pipe organ so we can hear the sound. So what we're going to do is for four different tuning forks, and the different tuning forks we'll be using, if you look at the lab, are 2048 hertz, 1024, 512, and 480. Right, now the relationship between this, for sound, in this case, the temperature is 20 degrees C, so if you look at the calculation, I end up with the speed of sound is 34,400 centimeters per second. And we're going to use centimeters because our measurements are in centimeters with the lab, as you'll see. All right, and then the relationship between frequency and wavelength is speed is frequency times wavelength. So these are all the frequencies, 1, 2, 3, 4. And so we can calculate what the wavelength would be, and the example would be, for the first one, would be speed over frequency, which would be 34,400 over 2048. I can calculate that to be 16.8 centimeters. Now for you then, I'm going to do the experiment. I have the data, but you're going to be calculating each of these yourself. So instead of 2048, use 10, 24, 512, and 480. So fill in the table, all right? And then what we're actually going to measure is in a tube, all right? So if you have a vibrating tube, like so, and we have a frequency, a tuning fork over it, like so, and we'll see that when we do the lab, we vibrated. If we have the right length here, all right, then we get, if we have a quarter of a wavelength, we get, this is lambda over 4. We'll see that if you read, that's a resonance. We're going to do that, but we want to do difference between 2 because there's a correction there. So then we do the next one of half a wavelength. All right. Oh, that's all right. Half a wavelength, which would mean we do this, okay, and this will be our second one. So this would correspond to half a wavelength, so D is lambda over 2. And so lambda then, will be given by 2 times D, all right? Okay. All right. So what we're going to do then is adjust the tuning fork. We'll see that when I do the lab, is just to get the first sound, and then we're going to raise the tube above the water so we get the second one, And this difference is what we're gonna call D. And once we have D, we'll then measure calculate what the wavelength is, compare it to our theoretical values. All right, so your theoretical values will be on the data table for the lab. We'll then measure the wavelength, and then we'll get the experimental one. All right, so experimental wavelength from there. All right, so that's the basis of the lab. So now I'm gonna go do the lab for you. All right, we are now going to do the experiment. We have the tube, and I adjust the level of the tube using this container of water. And as I raise and lower the tube, I will get the level I want. Now what we're going to be looking for is raise it up large enough so that I get the first sound, and then I get the second one, and so on. So I will, using the first tuning fork of all right, so this tuning fork, very small, at 2048, and I'll show you what I'm looking for. We'll start from the top, okay, and all right, so we'll start from down here. So those one's about here somewhere, and the second one's about here. So I'm gonna get the numbers, and then I will remember what they are. So $11.8 and 3.5. 11.8 and 3.5. So we'll write those on here. So we have the first sound at 11.8, the second one at 3.5, so the difference would be 8.3 centimeters. And that was with the 2048 tuning. So you have a very small tuning fork. That's our D is going to be 8.3 centimeters, right? Now next what we're going to do is the 1024 tuning fork. Okay. A little bit larger, and okay, they are theoretical. start from about here. $7.8. Right. 24.5. Yep. Okay. 7.8 and 24.5. Is 16.7. Yeah. So for the next one, the 1024 tuning fork, the lowest one was at 24.5. The next one was at 7.8 because we want to try and measure the difference between these two, and that's 16.7. All right, so that's with that tuning fork. All right, next one we're going to do is with the 512. Okay, it's even bigger still. I gotta hold it way out to get the whole thing in there. All right, so that's gonna be $16.50. Let's get an idea. Looks like 16.0. And 49. All right, now I'm not sure you could see it when I was doing that, but it was down at 49. So for the 512, we have 49 centimeters for the lower one, 16 centimeters, and so the difference is 33.0 centimeters. That's for the 512. And then finally, we'll do it for the 480. And the 480 is slightly bigger than the 512. And so we'll look at that one. That's a 17.2. Now the next one's 52. 1 and 17.2. All right, so for the 480, I get 52.1 minus 17.2 is 34.9 centimeters. So then I'll go through the analysis of the lab with you here after this, okay? We've now taken our data, all right? These are our sound tube measurements for the 2048, 1024, 512, and 480. So that's our measured D in this case. So that is what goes into column 2 of your sheet, are the measured D. And then we want to calculate, so I'll do an example with you here. So then, all right, so for the 2048, I went through this before, wavelength is 34,440 over 248, so we end up with 16.8 centimeters, right? Now our experimental one for that was D was 8.3 centimeters. So lambda is 2 times D, and this is our experimental lambda, E. This is our accepted value, we're calling now calculated or accepted, A, is 2 times 8.3, which gets us 16.6 centimeters. So that is what goes into the calculated value for the wavelength. So that's 16.6. We'll do that for all 3 of these. All right. So we calculate. So I'll write down what D again is. D for tuning fork frequency 2048, 1024, 512, 480. We end up with 8.3. This is D. This is the measured D. 16.7, 33.0, and 34.9. All right. So that is what we have for the measured value for the column 3 here. Calculated value will be 2 times that for the calculated wavelength, and that's what goes in column 4 is the experimental one. Now the percent error, all right, is going to be as accepted minus experimental over accepted times 100. So I won't work it out for you, but in this case, for this tuning fork, the accepted is 16.8. The experimental is 16.6. We divide all that by 16.8 and times 100%. So that gets you the percent error. So in this case, it should be relatively accurate. All right? So you'll do that and complete the table there and then answer the questions. And then there's 4 questions. All right? As far as these are concerned, all right. So you should be able to calculate those. And so question 1 deals with what happens to the wavelength as the frequency decreases. Question 2 is what would be the wavelength if we had a tuning fork with a frequency of 60? How much time does it take for one cycle? I'll go through that in a second. And then explain difference between longitudinal compression waves and transverse waves. What's the two difference? And what exactly is a sound wave? What type of wave is that? One question here, as far as the period is concerned. All right, so that's for calculating the lab. So, an example. All right, so if you have frequency, let's say I have a frequency of 100 hertz, the period in seconds is 1 over the frequency, so that'd be 1 over 100, or 0.01 seconds. So if the frequency is 100 hertz, the wavelength will be, not the wavelength, but the time it takes for each wave is 1 over that, or 1/100th of a second. So that is lab 7 for sound waves.